Hello, today I'm going to share with you guys a fun topic in physics that is reflection of wave. But before we started, let's watch a video.
Right, to start off we're going to need some water and we're going to fill that into about 5 mils depth. That should be fine. And then what I'm going to do is I'm going to add just a few drops of household detergent, and what that does is it reduces the tension on the water surface, which means that you can just make better waves. And I'm not going to try and make bubbles with that. I'm just going to move it around so it starts to mix with the water, trying not to make bubbles, because once we have the light on, any bubbles will show up underneath. And then to start off with, I'm just going to plug my light in. I can see the ripple tank isn't completely flat, so I need to adjust it so it is. I'm going to pull that leg just a little bit further in. This one. That one down a little bit. And there I have it completely flat. Now I'm going to use a power supply. And this halogen bulb takes 12 volts. Plug that in, and then we have our light on. I'm going to move that so it's in the center of the tank, over the tank. Now I can already start illustrating waves just by showing, for example, with this little pipette I fetched, just a single wave drop. And if you are working on a dark surface, you would want to put down a page over here so that you can clearly see the waves on the table below the ripple tank. So here I can make a little wave pattern, and they can see the little waves moving away from the drop. Then if I wanted to make a linear wave, a flat wave, I can use this bar over here. I'm going to put this into the water, and then without moving the whole tank, just move it back and forward like that, and then you can actually see the wave pattern underneath the tank on the surface. I can do that regularly to create the waves. Right, with the ripple bar, and so I'm going to connect that up over here. Connect it on the side, there we go. And hang that. Now I just want to, if I'm for example showing a single point, I'm going to have one of those pointing down then, and then I'm going to lower it until that ball is just touching the surface of the water. There we go. Then I can plug that into my speed controller, and that should turn on. And what I've done is I've got it on the minimum setting, and there I have that wave pattern in the water. Now I can use my barriers to illustrate, for example, what happens if I have that circular wave pattern and it hits a barrier at 45 degrees. And there they'll be able to see the wave reflecting off. Now if I wanted to show a straight wave, then what I can do is, let's just turn that off and turn that the other way, and then I'm going to lower it a bit so that the actual bar is just touching the surface of the water. There we go. Now below the tank they can observe how the waves are moving straight, hitting that surface, and then being reflected off it at an angle.
So, from the video, what is reflection of wave? Reflection of wave occurs when a wave strikes an obstacle. The wave undergoes a change in the direction of propagation when it reflected. From the diagram, we can see a wave reflect back after it hit a reflector that called obstacle, and the direction of the wave also change when it reflect back. Next, we move on to the wavefront. Based on the diagram here, all points along line AB are in phase of vibration and have the same displacement. Line AB, which joins the points in wave, is known as wavefront. Same like CD is also a wavefront. Next, bright fringes and dark fringes. When light rays move through water in a ripple tank, alternate bright and dark fringes can be seen on the screen. From the diagram, we can see the difference between dark fringes and bright fringes. The bright fringes correspond to the crest, while the dark fringes correspond to the trough. Next, there are two types of wavefronts that are plane wavefront and circular wavefront. The white lines in each diagram represent the wave fronts, while the red color represent the direction of propagation of the wave. For the plane wavefront, the direction of propagation of the wave must be perpendicular to the wavefront, while for the circular wavefront, the direction of propagation of the wave can be everywhere. For the explanation, the direction of propagation of the wave is perpendicular to the wavefront, and the wavelength is the same as the distance between two consecutive wavefronts.
Next, when the reflection of a wave occurs, as shown in the diagram, the angle of incidence must be equal to the angle of reflection. Other than that, the incident wave, the reflected wave, and the normal line must lie on the same plane. So, what are the effects of reflection on the characteristics of waves? Well, when reflection of wave happens, the wavelength, the frequency, and the speed of the wave remain the same and does not change, while the direction of propagation of the wave changes. Next is the drawing of a diagram for reflection of water waves. So, how do you draw a diagram for reflection of water waves? Well, step 1, draw an arrowed line AB which is perpendicular to the incident wavefront to represent the direction of propagation of the incident wave. Step 2, draw a line labeled BN which is perpendicular to the plane reflector. Step 3, draw an arrow labeled BC with the same angle as line AB to represent the direction of propagation of the reflected wave. And the final step, draw lines perpendicular to BC to represent reflected wavefronts. The reflected wavelength must be the same as the incident wavelength. Last but not least is the application of reflection of waves in daily life. For example, radio waves from communication satellites are reflected by the parabolic dish and focused onto the antenna on the feed horn. Next, ultrasonic waves are used in the medical field to examine a fetus or other internal organs. Other than that, technology of ultrasonic reflection, which is also known as sonar, helps to detect areas which have a lot of fish. Transducer transmits waves into the water, and these waves are reflected by the fish to the transducer, as shown in the diagram. Finally, patterns of reflected sound waves caused by different rocks enable the location, depth, and structure of the seabed, which contains source of natural gases, to be identified. So, finally, we have the example question. So, the question given is ultrasonic waves of frequency 25 kHz are transmitted from a ship to the seabed to determine the depth of the sea. These waves travel at a speed of 1500 meters per second in the water. Time between sending the ultrasonic waves and receiving the reflected wave is 120 milliseconds. So the question wants to determine the depth of the sea and the ultrasonic wavelength. So the first step, we must list all the given quantities, which is V, 1500 meters per second, the time, which is 120 milliseconds, and the frequency, which is 25 kilohertz. So after we list the given quantities, let's move on to A. So for A, we must use the formula V equals to 2D over T. So why 2D, you ask? Well, because the ultrasonic waves from the ship travel to the seabed and back to the ship, which means it travels twice the distance from the ship to the seabed and finally back to the ship. So we must substitute the given quantities, which is V, 1500 equals to 2D over 120 times 10 to the power of 3. Why? You ask, because it is given in milliseconds, so we must convert it back to seconds. So finally, we do the calculations. So after the calculations, the final answer will be 90 meters for the depth. Now, moving on to B. So for B, we must use the formula, which is V equals to F lambda. After that, we must substitute the given quantities, which is V, 1500 equals to frequency, but which is 25 times 10 to the power of 3, because it must be converted to hertz. And finally, after doing the equation, the final answer should be 0.06 meters.